I did my master's in 2002 in University of Madras. After that, I moved to IISc Bangalore to do my PhD. I did work on synthesis of new organic molecules. I completed my PhD in 2006, and then I moved to US for doing postdoctoral research. There I did my first postdoc in Pittsburgh, and then I moved to Yale University, New Haven, and I completed 3.5 years there. Then I got a job in IIT Mandi as assistant professor. In the year 2010, I joined IIT Mandi. Since 2010, I have been teaching here chemistry for BTech students. Now I would like to go to the topic. So before I begin the lecture, I would like to address a very important question, which normally students ask me when I go to my first class. So why should I study chemistry? I joined engineering course, so why should I study chemistry? Usually I ask them back a question, what is engineering? So usually they say that engineering, electrical engineering is about study of electrical sciences and different things. But I ask specifically what is engineering, but usually there's no answer. But the answer is engineering is nothing but it's just an applied science. It's an application of science. So basically we cannot separate science from engineering. So that's why these science subjects are introduced at the very first year level for engineering graduates. To give an example of why we need to study science, I just want to give a very old example that Ohm's law was first introduced in 1828, and after several years, after some time, Edison discovered incandescent bulb, which is an application of Ohm's law, and also an extension of this black body radiation. So he basically used science to discover this incandescent bulb. Basically, he just tried to find different materials which can have high resistance. If there is a high resistance, you can have very low currents passing through it. And he found an optimum material which can get heated up. And as per black body radiation, we know that if it's heated at a very high temperature, it emits visible radiation. That's how this lamp was discovered, and it's a remarkable achievement. And even till today, it's even after 150 years, we know that we are still using this filament lamps. Now it's slowly disappearing because of advancement in LED. LEDs are replacing filament lamps largely. Even LEDs is also the materials that used are basically chemicals. And in fact, one of my colleagues is working at IIT Mandi is trying to make some materials which is better than currently available materials. So the point here is we cannot really separate science from engineering. So a basic understanding of science is very essential for engineering graduates. Just to give you an idea, as engineers, when you go for a job, you will take up different jobs where you basically have to use the materials and come up with different products. Just to trigger your curiosity, so I have put some of the interesting questions which is happening in your day-to-day life, but you generally don't bother. But there is an answer, chemistry answer for these questions. Chemistry is basically involved intimately in your daily life, right from brushing your teeth in the morning to having your last meal before you go to sleep. The chemical which you use for brushing your teeth is actually a chemical, and the meal, the food that you are using is also a chemical. The food that you use is also a chemical. So You can't really interchange the two. You can't eat toothpaste for your food, or you cannot use your regular meal for brushing. So each function is different. The chemical which is used for toothpaste is different from what you eat. The function of these chemicals is determined by the structure of the molecules. Just to give you an idea, I have put a picture in which you can see a lot of these vegetables. Basically all these are organic molecules, they are carbohydrates basically, and they have different combinations, gives rise to these kind of different colors, textures, and all these kinds of varieties, but basically they are chemicals. And as I told before, the function of organic molecules or chemicals is intimately associated with its structure. And the structure of the molecules is due to the bonding between the different atoms in a molecule. Therefore, it's very important for us to understand the fundamental principles that govern both the structure and bonding present in the molecule, because these two largely decides the function of any molecules, and so that means the application of any chemicals. That's why we are studying this topic, structure and bonding in organic molecules. By understanding the structure and bonding present in a molecule, we can understand the reactions that it can undergo. As I just said, if you understand them thoroughly, you can understand its function. Almost every molecule will have a structure and a functional group. Almost every molecule. I'll give you some examples. This is the pictorial representation which tells that how a molecule can have two parts. One is a functional group part, which tells how the molecule will react, and another part is the carbon framework, which gives the structure to the molecule. The simplest of all the molecules is methane. Here I've shown ethane. It's a molecule with two carbons and 6 hydrogens in it. This is basically a hydrocarbon. Generally hydrocarbons are considered as having lack of functional group. The little bit higher hydrocarbon is cyclohexane. If all the carbons are connected in a circular fashion, then it gives a cyclohexane. This kind of structural variations gives rise to another kind of properties called stereoisomeric properties. These molecules can exist in different stereoisomeric forms. That means the structure is deciding how they are going to be exist in different forms. Here there are some other examples: acetylene, formaldehyde, acetone, and methylamine. Acetylene has a triple bond, carbon-carbon triple bond. This is a functional group because triple bond are known to undergo several reactions. So this CC triple bond is a functional group which impacts reactivity to this molecule. And here, in acetylene is commonly used as a gas for welding purposes. Formaldehyde is another important molecule. In this, there is a carbon-oxygen bond, double bond. There are a number of reactions that a carbonyl group can undergo. So the carbonyl group is the functional group in this molecule. And formaldehyde is also used in many polymer preparations as a starting material. For example, bakelite, which is urea formaldehyde polymer, which is the starting material is basically formaldehyde. And acetone is also used largely in industries. Here again you have a carbonyl group, which is the functional group which determines the reactivity of the molecule. And methylamine is another molecule which has a carbon-nitrogen bond and NH2 bonds. There are some reactions that it can undergo, and these are used as a starting material for so many drugs that you use. Drugs, what I mean by drugs is all the medicinal compounds that you take as in tablets, basically organic molecules, and most of them are nitrogen containing molecules, and they need to be prepared in the lab, and these kind of starting materials are used in those drugs. So as I said, the functional group determines the reactivity of organic molecules. Hydrocarbon, even though it is not a functional group, it also undergoes some type of reactions. It can undergo a photochemical chlorination reaction. Under photochemical conditions, it can generate chlorine can generate chlorine radicals, and radicals are reactive species. It can replace the hydrogen and form methyl chloride. Methyl chloride is a molecule which has a functional group now. You have now chlorine. Chlorine is a functional group. I will show you what kind of reactions that methyl chloride can undergo. Methyl chloride can undergo a substitution reaction. This, for example, the chlorine can be replaced by iodine to get methyl iodide. This is another molecule with iodine as a functional group. And iodine can undergo some reactions. For example, elimination reaction. If you take ethyl iodide, you can, if you treat with potassium hydroxide, this is a highly basic, strong base. Under the influence of a strong base, it can undergo elimination and give this another molecule with a different functional group. So just by manipulating this functional group, you can make different molecules. If you have iodine, you can actually make a double bond next to between the two carbons. If you have simple hydrocarbon, you can actually replace one of the hydrogen with chlorine. If you simply have chlorine, you can actually replace with iodine. These are several types of possible reactions that the molecules undergo. Then the question can arise that what is the use of all these things? The use of all these things is that by understanding the functional group and its reactions, we can make the molecules that we want. And the first ever organic molecules that is synthesized in the lab was way back in 1829 by Wohler. He synthesized urea, this is urea, from lead cyanate. On those days, it was believed that organic compounds, carbon containing compounds, are prepared only by living systems, and that's how the name came organic, because all the living systems like bacteria, humans, even human beings, we all made up of organic molecules. So it was believed that organic molecules can be made by only living systems. Urea was found first discovered in human urine. I don't know if you have noticed, in urine test in hospitals there is a column, you will find that urea percentage. So urea is present in urine. It was first discovered in 1820s and somebody crystallized it and found out the chemical composition. The same urea was later synthesized by Wohler. This was the first molecule it was synthesized. Now you might ask, what's the need of synthesizing urea if it is secreted in this thing? You'll be surprised that urea is a very urea is produced in tons and quantities in all over the world, and it is a major fertilizer in agriculture. And at that time when it was synthesized, it was not known what is its application, but later it was found that urea actually helps to a plant crop to grow faster. You see the impact. Somebody synthesized a molecule, don't know what it is used at that time, but later it was found that it is very useful, and now it's a multi-billion industry. So, and it helps to improve the quality of our lives. And not only that, urea is also found application in making plastics, as I just said some time back, that if you mix urea and formaldehyde, you can make a polymer, and these polymers are hard substance which can be used as a frame for different objects. Here I've shown, for example, clock with the body is made of this plastic, hard plastic, bakelite. So a synthesis of organic molecule is also a very important area. Here are some of the molecules which are synthesized by chemists in the lab. So this is benzyl penicillin. It was originally found found to be secreted by a fungus, and it was found to have antibacterial properties. And now it's antibacterial. It is used as an antibacterial drug, and it is synthesized in the labs, and it's produced in large scales. And saccharin is an artificial sweetening agent, and it is also was synthesized in the lab, and now it is it's a big industry which produces saccharin. And chemists also were creative, and they also tried to make some fancy molecules. This is cubane. It's just like a cube, and they tried to study the bonding nature between the carbon. These are highly strained molecules. It helps them to study the bonding nature present in these kind of molecules. So synthesis is a very important field which helps to create more and more new molecules to improve the quality of our life. Now I would like to go through from the very fundamental concepts, because it's very important to be very strong in fundamental concepts. So it's very important, before we go further, it's very important for us to understand the nature of a chemical bond, what keeps the two atoms together. So the simplistic approach of understanding a bond is can be understood by Coulomb forces. It's based on the two important principles. One is opposite charges attract each other. That means electrons are attracted to protons, and like charges repel each other. Electrons spread out in space. Since the electrons are like charges, they are spread out in space. And this is the basic law. Coulomb's law states that the attractive force between the two charges, positive and negative, is equal to a constant multiplied by the charge, the product of charges, and the square of its distance. And in simplistic terms, we can understand a bond, covalent bond, by just by looking at the structure of atom. Atom consists of electronic cloud around the nucleus. Nucleus is the concentrated positively charged center, and the electrons are surrounded by it. In when two atoms come closer to each other, what happens is the positive charge of one atom tries to attract the negative charge of the other atom. Similarly, the positive charge of the other atom attracts the negative charge of this one. Then what happens is, when they come closer, the influence is so great that they both come to an optimal distance, and then they stop there. They don't further go closer, because if they go further closer, the repulsion forces dominates, and so the energy level increases. So they don't go further closer, and the optimal distance at which they stop coming closer together is called as the bond length. And it will become very clear by the next slide. It's clearly shown here that this is the energy axis, and this is the internuclear distance axis. And you can presume that when the two atoms very far apart, let's say here it's very infinitely far apart, then there is no difference in energy. Both are happily staying together. I mean, both are happily independent of each other. And as it comes closer and closer and closer, you can see there is an energy drop. The drop in the energy is due to the attractive force that between the positive charge of one atom and the negative charge of another atom. So, and the attractive force, when it becomes closer and closer and closer at an optimal distance, the energy drops way lower, and after that it increases, because the repulsive forces dominates after that point, stay together. And when this amount of energy will be released when they are brought to this distance, and that distance is usually called as bond length, and the energy between this level and this level is called as bond energy. Bond energy is basically the amount of energy released when the two atoms are brought together and made a bond. Now the depth of the bond, the depth of this well tells the strength of the bond. If stronger the bond, the more will be the bond energy, more will be the energy released. The weaker the bond, the less will be the energy released. Now I would like to give you an activity. Presuming that the above diagram to be an example of a strong bond, draw the diagram for a weak bond. So just take a few minutes and then try to draw the diagram for this. I will also draw the actual diagram, but just take few minutes. Meanwhile, I'll go and pull the next slide. So now I will write, I hope you might have thought through this, and now I'll draw the diagram for a weak bond. So as I said, if we draw the strong bond first, suppose presuming that this is for strong bond, it was like this. It went down all the way down, and then it went down. Suppose if this is considered as a strong bond, then as I just told also one more thing, this distance tells the energy released. This is energy axis, and this is internuclear distance. For a strong bond, the energy released will be greater, which obviously means for a weak bond, the energy released should be less. So all that I need to do is I need to draw a diagram where the energy released is less. So if I just take the same scales, then for a weak bond it will be just like this. So you can compare these two, that this will be the diagram for a weak bond. This will be less. The energy, obviously the distance here is less, so this is a weak bond. Okay, so I'll go to the next slide now. Hope you all understood. If you have any doubts, I can address the doubts at the end of this session. Okay, and now I'll talk about the octet rule. Atoms tends to form molecules in such a way as to reach an octet in the outer electron shell. Octet configuration can be achieved either through pure ionic bond or through pure covalent bond. What it tells is that if there is an atom which can lose electron, to form an octet configuration, it would rather lose an electron. And if there is an atom which by gaining an electron can form an octet, it will rather gain electron and form an octet. Here the extreme right hand sides, these are octet configurations where the shells, the energy shells, are quickly filled with electrons. These are usually inert elements because they completed the octet. They generally don't take up electron or either lose electrons. They are stable configuration. Whereas if you see here, fluorine, which is 2 electrons in the first shell, second shell has 7 electrons, which is one short of octet configuration. So fluorine is a highly electronegative atom. It wants to readily take up an electron. Similarly, if you see here, lithium, which has the first shell complete octet 2, similar to helium, and after helium configuration has 1 electron in the valence shell. So lithium would rather like to give up this electron and go back to this helium configuration. So lithium generally wants to give up electron, and fluorine generally wants to take up electrons. All these halogens which has 1 electron short of the octet configurations, they are electronegative. Generally they want to take electrons. All these elements in the first group, all of them are having 1 electron extra after the octet configuration, so they tend to give up electron. So just to emphasize this point, if sodium, as I said, they are electropositive, it has 1 electron in the outer shell which it wants to give up to become Na+, which is actually a neon configuration. This process is associated with we have to supply energy, only then this will happen, because this is in gaseous state. Chlorine, it also wants to take electron and become an octet configuration, argon configuration in this case. This is a exothermic process. Suppose if sodium and chlorine were brought together, sodium just readily gives electron and chlorine readily accepts electron, and the total energy in this process is calculated as 36 kilocalories, which is positive, which means this is for this process to happen you need to supply energy. This is quite contradicting. In actually reality it is an exothermic process. The discrepancy can be explained by this attraction, Coulombic attraction between sodium ion and chlorine ion. Once sodium loses electrons and chlorine picks up electrons, these two are now oppositely charged, and there is a Coulombic attraction between these two ions, and that energy is equal to 120 of 120 kilocalories. And now actually you can see that in reality, if you take sodium and treat with chlorine, and the energy released is 84 kilocalories. That's basically the difference between 120 and 36. It's an exothermic process, and since both are oppositely charged, the Coulomb forces tend to retain these two ions together, and the bond is called as ionic bonds. So in pure ionic bonds, octets are formed by transfer of electrons. That means electron from one atom completely gets transferred to another atom. Let's now see the electron dot representation, how it is represented by electron dot representations. This is the partial periodic table, and the valence electrons I have just showed here, only the valence electrons. For example, lithium has 2 electrons in the first shell, and the valence shell has 1 electron, so we just put 1 dot here. Similarly, beryllium has 2 electrons in the valence shell, so it's 2. And for fluorine, 7 electrons in the valence shell, so it is 7. We can show the ionic reactions by electron dot picture. For example, if sodium with the valence electron 1 combines with chlorine with a valence electron of 7, you can see here that 1 electron gets transferred, as we just saw in the last slide. It becomes sodium chloride. And similarly, magnesium, it's here the valence electron is 2, so it is 2 electron, and chlorine, which has 7 electrons, they both can combine. Magnesium can lose 2 of its electron to become octet configuration. Magnesium's octet 28, which is basically neon. So magnesium would tend to give 2 electrons and form neon configuration and remain as Mg2+. Chlorine would like to take these 2 electrons, 1 electron each, and become 288 configuration, argon configuration. So both are now in octet configuration, and so both are stable since they are charged, oppositely charged, and the forces that bind together is purely ionic. So now I would like to ask you to just take a few minutes and draw the electron dot picture of these elements. It's a good exercise because it gives you a clear idea of how the electron is involved in the bonding, and how it is in why in some cases it is getting transferred. Just take a few seconds. Meanwhile, I'll pull out the next slide. The first was I will write for lithium bromide. Okay. And lithium, we all know, is an electropositive element, and it has got 1 electron in its valence shell. So let us first write the lithium with 1 electron, plus bromine has 7 electrons. Now lithium, as we all know, wants to give away electron. So lithium will form a positive charge, and then bromine will take up that electron and form this octet, and this is forms Br minus, negative charge. And now I'll write for Na2O. Sodium is also similar to lithium. It has 1 electron in the valence shell. Oxygen has 6 electrons in its valence shell. No. Yeah, 6 electrons in its valence shell. So you have 2, 1, 2, 3, 3, 4, 5 and 6. 2 sodium is involved. So 2 Na, no, sorry, we have to write it in box. So sorry about this. So this is the way for sodium oxide, and you can also do for beryllium fluoride. So beryllium is a group 2 element, so it will have 2 electrons in the valence shell. Fluorine is a halogen, it will have 7 electrons in its valence shell. 1, 2, 3, 4, 5, 6, 7 electron. Since 2 fluorine atoms are involved, I'll write 2. So beryllium fluoride, we can write beryllium 2 plus, and then again, since more than one atom is there, you have to write square brackets 2 ions, and it becomes negatively charged. So in the same way, you can also write for aluminium and MgS, I think, so that you can take as a take-home assignment. So now I will go to the next slide. Now I will talk about the covalent bonds. In covalent bonds, electrons are shared to achieve the octet configuration. Unlike in ionic bonds where the electron is completely transferred from one atom to the other, in covalent bond both are equally strong. Both doesn't want to lose its electron, so they strike a compromise, and they say let's share with each other. So both equally 1 electron each and form a covalent bond. The classical example is a hydrogen atom, where you can see that the 2 electrons are shared nicely between the 2 hydrogen atoms. So the 2 electrons are shared between the 2 hydrogen atoms. Similarly, in hydrogen chloride also, the 2 electrons are shared between the 2 atoms. So in this way, hydrogen, in order to reach its octet, it needs 2 electrons. Here it's 1 electron from this hydrogen, 1 electron from this hydrogen, so it's shared, so it reaches its octet. Similarly, this hydrogen also reaches its octet. In this case of HCl, hydrogen reaches its octet by having this shared pair of electrons. Chlorine also reaches its octet, 8 electrons. Octet, the reason the name octet came because this the second row elements, all of them actually have 8 electrons in their valence shell, can accommodate up to 8 electrons in its valence shell, so that it can reach octet configuration. Chlorine, you can see here there are 8 electrons around it, so chlorine also could able to achieve its octet. So similarly, a bond between chlorine also is the same way. You can explain as I explained in the first 2 examples. So both of them are able to achieve octet configuration. Similarly, for methane, ammonia and water, all of them you can write electron dot formula and show that all the atoms can achieve octet configurations. In the case of ethylene, you only have 2 carbons and 4 hydrogens, and all of them have to achieve octet configuration. So the best way is carbon can share 4 electrons, means carbon can share 2 of its electron with other, each one shares 2 electrons, so it can form a double bond which requires 4 electrons. Ethylene is another good example where it can each atom can share even 3 electrons, up to 3 electrons, and form a triple bond. So, and they can comfortably achieve octet configuration in both cases. You can see here this carbon has this 6 electrons due to this triple bond, and 2 electrons due to this single bond with hydrogen. So in total 8 electrons. So it has achieved its octet configuration. So that's why acetylene is a stable molecule. So now just take a few minutes and then draw the electron dot picture for fluorine. Then you will be able to understand it little bit better. So I will just go to the create a slide, and then I'll take a couple of minutes to draw the electron dot formula for covalent bonds of fluorine, CF4 and CH2Cl2. Suppose if we draw, then now we draw the electron dot formula for fluorine. I hope now you all can easily do, because I have been telling fluorine has 7 electrons. 1, 2, 3, 4, 5, 6, 7. Another fluorine atom with 7 electrons. So both will combine and they share a pair of electrons between each other, and all of them achieve 8 electrons in its valence shell. So thereby both achieve octet configuration. The same you can put for CF3, CF4 as well. Carbon has 4 electrons in its valence shell, and fluorine, we know that it has 7 electrons. So 4 fluorines and 1 carbon. Obviously carbon can form 4 bonds octet configuration between 4 fluorine atoms. So this way we can explain the covalent bonding between the atoms by sharing the electrons between the 2 atoms. Now let's go a little bit further and talk about the polar covalent bonds. The ionic bond and the covalent bond which I talked about were two extreme cases. In ionic bond there is a complete transfer of electrons. In covalent bond there is not, but it's just shared between both of them. But in reality there are many molecules in which it is in between these two extremes. Some ionic bonds are having covalent character, some covalent bonds having ionic characters. So now we will see covalent bonds that have polar characters. Supposing to understand it better, we need to first understand the concept of electronegativity. Electronegativity is a property of an atom which would like to pull the bonded pair of electrons towards itself. The tendency of an atom to pull the bonded electrons towards itself. This is called as electronegativity. Since we know that fluorine is highly short of one electron short of the octet configuration, it's always in need of electrons. So whenever there is an opportunity, it tries to pull the electron towards itself because it's one short of octet configuration. So if fluorine forms a bond with oxygen, so fluorine would tend to pull the electron because fluorine is more electronegative than oxygen. So the electronegativity scales are shown here. This is a partial periodic table. So fluorine was set as 4 and the lithium is kept as 1. This is a relative scale. Lithium being less electronegative, or in other words it's more electropositive, it tends to, that scale is set as 1. With reference to lithium, fluorine wants to take up 4 times better. It keeps the electron, keeps with it 4 times better than lithium, who tends to keep electron with itself. Just by seeing the scale, the electronegativity nature, you can see here, it is increases from down to up, and it increases from left to right. Electropositive character is exactly opposite. So electropositive character increases down the group of on the left side, and it decreases from left to right. So when you form a bond between the two atoms whose electronegativity values are not very different, then you more or less form a covalent bond. But if you form a bond with relatively good difference, let's say hydrogen fluoride, so the electronegativity difference is quite good. So the bonded pair of electron between hydrogen and fluorine is moved towards the fluorine atom, as it is shown here. So even though hydrogen and fluorine forms a covalent bond, the covalent bond is kind of polarized towards more, the negative charge is more polarized towards the fluorine atom. So as a result, it can be shown with this delta positive and delta negative charges. The same can be explained with ICl, CF bond, because the carbon and fluorine, the electronegativity scales are 2.6 and 4. So if that bond will be more polarized towards fluorine, and it is shown as delta minus and delta plus. The same can be explained here for the methanol as well. And generally this is calculated, the polarization is calculated as in terms of dipole moment value, and if the electron density is on this direction, here in this case oxygen is more electronegative, so it's delta minus. The arrow is shown generally like this. This arrow side shows the electron rich side of the molecule. So now I would like you to do a small exercise wherein you can draw molecules and combine any atoms, and you can predict, just by seeing the electronegativity values, you can predict which way the dipole moment is for the different molecules. And it's not always necessary that if a molecule has got a polar bond, that the molecule will have polarized dipole moment, because it's quite possible that even if a molecule has a polar bond, that if the two bonds are exactly opposite to each other, then the dipoles cancel each other, and the net dipole moment of the molecule will be 0. The good example is carbon dioxide, which is a linear molecule. Even though it has two polar bonds, they are in the exactly opposite 180 degree to each other, so they both cancel each other and has no dipole moment. Another good example is carbon tetrachloride. Here again the bond is polarized, but since all the bonds are exactly opposite to each other, the net dipole moment of this molecule will be 0. Just to quick exercise, just to show the just take a few minutes of your time and try to draw the bond polarizations for water, IBr, methane, chloroform, dichloromethane and CHCl3. I'll give you few minutes time so that you can draw it for yourself, and then as I'm going to write it anyway, you can compare your results with my values. Is a polar molecule. It has a bent structure. Now you'll in the next slide I'll be able to explain why it's having a bent structure, but for the moment you just presume that water has a bent structure. So water is a bent molecule. So since oxygen has got greater electronegativity value than hydrogen, hydrogen is 2.2, oxygen is 3.6, about 3.8. So here it's clearly the bond polarization is this direction. Similarly here the bond polarization is this direction. And in IBr, iodine is down the group. Chlorine, fluorine, chlorine, bromine, iodine. So iodine comes down the group. So as when I showed the electronegativity table, I showed that down the group electronegativity decreases, which means iodine has lesser electronegativity than bromide. So we can easily draw, in this case, the dipole moment direction is in this direction. Similarly, you can draw for methane, chloroforms, and dichloromethane and methyl chloride. I'll just here show only for methyl chloride. So methyl chloride can be drawn like this, and the dipole moment is in this direction because chlorine has more electronegativity than carbon. Now I'll talk about the structures, how the electrons bonding and the lone pair of electrons present on the molecule affects the structure of the molecule. The simplest example I would like to discuss is the beryllium fluoride. Beryllium fluoride is a linear molecule, but it can also have a bent structure, but it was found to have a linear molecule and not a bent structure. This can be explained by this theory. Molecules adopt shapes in which both bonding and non-bonding electron repulsions are minimum. So they try to adopt shapes in which there is minimum repulsion between the bonded and the non-bonded electrons. And if you draw the electron dot formula for beryllium, you will see that it requires 4 octet. So you will have one shared between the two, you have one bond with fluorine, another bond with another fluorine, so that way it have 4 completes 4 configuration. It means it will complete to it will able to complete its valence shell. Similarly, fluorine also is able to complete its valence shell. So, and beryllium doesn't have any lone pairs. As you can see, there is no dotted pairs here. So the best way this can exist, this molecule can exist to avoid repulsions between the two bonded electrons, is linear arrangement. If the two bonded electrons are straight opposite to each other, then there is less repulsion between the two. Whereas if there is an angular bond, there is a closeness between these two bonds which is not favorable. So this is much more favorable compared to, because this is far apart, and that's why beryllium fluoride tries to is adopting linear structure than angular structure, bent structure. In BCl3 you can draw the electron dot formula, and you will find that you can only put 6 electrons in its shell. It cannot have extra pair because it doesn't have sufficient electrons with it. So if it has only 3 bonds and no lone pairs, then all the 3 bonds can exist as a triangular fashion, like trigonal fashion, to avoid electron repulsions between the 3 bonds. If it adopts this one, then there is electron repulsion between this and this one. So it prefers to have trigonal structure. So what really determines the structure is basically the electron repulsions between the bonded pair and bonded pair electrons, lone pair and the bonded pair, and the lone pair and the lone pair. So methane, for example, has got 4 bonds here, 4 carbon hydrogen bonds. In fact, you can write this 4 carbon hydrogen bonds like this, in fact, but carbon hydrogen hydrogen hydrogen, like a square type of thing. But in reality it doesn't it is not a planar structure. It is actually a tetrahedral structure. Why? Because in planar structure the angle is 90 degrees, whereas in tetrahedral structure the angle is 190 degrees, which 190 degrees means they are far apart. So it is 190 degrees between any 2 bonds, whereas in planar structures it's 90 degrees between any 2 bonds. So obviously 109 degrees is actually it's a 3-dimensional structure. It actually provides a longer distance between the bonds. So that's why methane exists in tetrahedral structure and not as a planar square type planar structure. Now I just want to ask you, based on what information I gave, just to try to explain why ammonia is not trigonal but pyramidal. Trigonal means flat and 3 atoms. For example, if ammonia were to be trigonal, it has to be like this. It has to be like this. But it is not trigonal. Trigonal is not present. It is existing as pyramidal. It is angular. Nitrogen is up and the 3 hydrogens are projecting down. This you can explain if you start writing the electron dot formula for the nitrogen, ammonia. Then you will be able to explain based on this theory that bonding and non-bonding electron repulsions should be minimum. The same is the case, you can explain why water is not linear but bent with a dihedral angle of 104.5. So now please take a couple of minutes and think about it. You can also discuss with your colleagues and think about this problem and why it is so. Now I'll go to the next slide. Just take a couple of minutes and just think about these things. So So now I'll explain why ammonia is pyramidal. If you draw the electron dot formula for ammonia, this is how you can write. So it's clearly having one lone pair electron and three bonded pairs. Lone pair as per the rule which we saw in the last slide, molecules, which clearly states molecule adopts shapes in which both bonding and non-bonding electron repulsions are minimum. So if you go by that rule, so there should be minimum repulsions between this non-bonded pair of electrons and the bonded pair of electrons. That means, as we have seen in the example of if you adopt a planar, this is a lone pair, let's say this is a lone pair and this is a bond, this is a bond. Suppose if you take a planar structure, then the angle is 90 degrees. If you take an angular structure, where the tetrahedral structure, wherein nitrogen takes one corner of the tetrahedron taken by the lone pair, and this hydrogen takes one corner, that hydrogen takes one corner. If you take tetrahedral structure, then the angle is close to 109. Here in the case of ammonia, it is 107.3 between the two bonds, not between the lone pairs, between 107.3. What it means is the angle between this and this is greater than 109. So it's not exactly tetrahedral, it's kind of distorted tetrahedral, wherein the lone pair to bonded pair repulsions are higher, so the angle is higher, and that is partially compensated by a smaller angle between the bonded pair and bonded pair electrons. So angle here is 107.3, which is better than having a 90 degree of angle between the two bonds. And so ammonia takes pyramidal structure. And this is not trigonal. If you want to have trigonal, this is exactly what is trigonal. Then you will not have any place, if all these things are in plane, they will not have any place to put the lone pair. Of course you can put the lone pair vertically above, but that will still be, the angle will still be lower than this pyramidal structure, because if it's vertical, then again, if you suppose, let's say this is vertical, then again this will be 90 degrees. So then this will be, when compared to that, pyramidal structure will have better distance between the lone pair and the bonded pairs compared to trigonal structures, and that's why ammonia is trigonal and not pyramidal. The same arguments can be applied to water as well. For example, water exists as a bent structure and not as a linear structure. This can be understood by Lewis diagram. So if you write the water Lewis structure, it has two lone pair electrons and two single bonds. So if we have to accommodate the two lone pairs as far as possible. So if you put the two lone pairs, let's say you write these two lone pairs like this loop and the two bonds, again this has to adopt this tetrahedral structure, and each lone pairs and atoms will be accommodated in each corners of the tetrahedron, and so you will have angular structure. And here it is said that the angle is 104 degrees, and which is much less than 109, which means the lone pair repulsion is higher, which is basically pushing the two bonded pairs to come closer. So that's why the angle between the two is lesser than the tetrahedral angle. So it's also a distorted tetrahedral structure, water, but largely it is explained. It is told as it has having bent structure. Now we'll go to the next slide. Now I'll just say a few simple rules for drawing the Lewis structures. Very simple. Let's consider the example of methane. Methane molecule has got 4 hydrogen atoms bonded to one central carbon atom, and you can draw like this methane. So first we need to draw the molecular skeleton. For methane you have to draw like this.
count the number of available valence electrons, add all the valence electrons of the component atoms. Special care has to be taken with the charge structures. So by this, what I mean is, carbon has got, there is a difficulty here because I can't show the rules, and parallelly I can't draw because there is a third rule. Okay, I can draw in the bottom. So as per the second rule, carbon, for example, we need to count the number of valence electron. Carbon, we know it has 4 electrons, so it has 4 electrons. Hydrogens has 1 electron each, so it has, since we have 4 hydrogens, for oxygen the number of valence electron is 6. the number of valence electrons 6 minus number of lone pairs, it has 4 lone pairs. And the number of bonding electrons here in this, I'm sorry, generally oxygen has got 4 lone pairs, but here in this molecule it has only 1 lone pair. So then I need to write only 2 electrons here. So 2 electrons, and the number of bonds, it has 3 bonds, so it has total 6 by 2, that is 3. So 6 minus 2 minus 3, that is 6 minus 5, that is plus 1, that is 1. So oxygen is the one which can carry the positive charge in these molecules. So whenever there is a charged species, if you have to decide on where to put the positive charge, this is the rule that you need to follow, that you need to apply all the first three rules and find the electron dot formula, and then use the fourth rule to find the positive charge. If you have any questions regarding this, we can discuss about this at the end of this session. Now I'll go to the next point, and just wanted to ask you to think about molecules for which octet rule does not hold true. I can give you a quick example. BH3 is a good example for which octet rule doesn't apply. Just think about this, why it is so. Then if you have any doubts, then we can discuss about these things in the later. So all these things points to one thing, that even though we have tried to understand the electron bonding, for bonding we need 2 electrons from between the 2 atoms, for ionic bonding transfer of electrons, and we have so many rules. This octet rule, we found that it's an observation, it's not a rule, it's an observation, that if there is an octet arrangement on an atom, it's found to be stable. So that's how this rule has come. But there seems to be some exceptions as well, like just I explained BH3 is an exception. So there are so many other molecules which nitric oxide also doesn't follow this octet rule, which means the theory that you have now, until now, means up to now what we discussed, is not enough to explain everything about bonding, which means this is a lower order theory. This theory is a very primitive theory, so we need much higher level theories to really understand the bonding present in the molecule. So, and I will be discussing about that in great detail in the next class. That's the reason why I had to really talk about every little things that we already know. But in the next class I will be able to talk to you about the molecular orbital approach of understanding bonding present in the molecules, so which is a much higher level theory compared to this one. So before that, I would like to also talk about resonance forms. After this I will conclude the class. It will take about 5 to 10 minutes. Resonance forms, for example, suppose if you try to write the Lewis structure, electron dot model for carbonate ions. We just discussed hydronium ion, H3O plus ion. If you try to use this Lewis acid rules and write the structure for carbonate ion, you will be able to come up with this structure, which is shown here. Actually, the interesting thing with this structure is, since all this molecule is symmetric and it has 3 oxygens, you can actually push the electrons. It's shown here, electron pushing is shown here. You can actually push the electrons in this way and concentrate the negative charge on this atom instead of this atom. Similarly, you can do this one more round of this electron pushing, and you can bring this negative charge on this atom instead of this atom. So this kind of thing you can do, and you will find that all these 3 structures are equivalent, and in reality the molecule is somewhat like this. This single bond has partial double bond character. Suppose if one of the structure were to be true, then if you have recorded the spectra, if you have recorded the bond length of this carbonate ion, one bond should have a double bond length and another bond should have single bond length. Single bond is slightly longer than double bond. So in reality what they found was all the 3 bonds were somewhere in between single bond distance and double bond distance, which means all of them are equal, which means this kind of mechanism is operating. The negative charges is just going around and sitting on all the three oxygen atoms. So the effective resonance hybrid structure which we can write is this way. So each oxygen has 2/3 of the negative charge is shared, and the bonding is not a single bond and not a complete double bond, it's somewhere in between, so you can show it as a dotted arrows. So this kind of equivalent forms, we call it as resonance forms, and this is very important concept to understand many more organic reactions. So that's why I wanted to discuss about this resonance forms. There are some other resonance forms. For example, acetate ion CH3COO minus can also have similar type of resonating structures. Here the number of resonating structures is limited to only 2 because there are only 2 oxygen atoms. So that can be drawn like this. This is the resonance hybrid structure, where you write half charge is on one oxygen, another half charge is on the other oxygen. So this is how you can write the resonance structure. Another good example is propenyl anion, in other words allyl anion. You have 3 carbon atoms connected with the carbon having a negative charge and a double bond. Here again this electron pushing can happen and can give rise to 2 equivalent structures. Basically, if you see carefully, these 2 are equivalent structures. This carbon with a double bond has 2 hydrogens. Similarly, this carbon with a double bond has 2 hydrogens. The middle carbon always has 1 hydrogen attached, on one side double bond and on the single bond. You can see that. So basically these 2 are also an equivalent structure. As you can see here, the resonance tribit can be written like this, half and half. If you have equivalent structures and when you do reactions on that, then you will get products which is also similar, whether either form can react the same way and give rise to the same product. For example, the proton here can get attached itself to this one, then you will get this product. If the proton attaches to this anion, then you will get this product. So if you see these 2, both are same actually, both are same. So when you have equal resonance structures reacting, you will get the same product. Same is the case with the cations as well. These 2 cations are equal. When you when hydroxyl ion attacks this carbocation, you will get this product. If this hydroxyl ion attacks this carbocation, then you will get this product. But both are same. So when you have equivalent resonating structures, you will get the same product. However, there is no need that all the resonating forms should be equivalent. The good example, I'll discuss about the nitride ion later. Good example is enolate anion. The enolate anion, you will see that if you do the electron pushing, the negative charge is centered on carbon here. Here the negative charge is centered on oxygen. So these 2 are not equivalent resonating forms. So in such cases, we cannot write this kind of resonance hybrid structures and say that half of the time this is in oxygen, half of the time this is in hydrogen. That is, you cannot draw that because these 2 are different structures, so you cannot draw such a resonating form, which means the reality is one of the anion, one of the charges, one of the forms is dominant over the other. So that's the reason why you cannot write this equivalent picture. I'll show another example of non-equivalent resonating forms. Formaldehyde, a neutral molecule exists like this, but you can also do a charge separation and separate the negative charge towards the oxygen, positive towards the carbon, and show it like this. And between these 2 resonating forms, you can write both octet as well as non-octet resonating forms. Same is the case you can explain with sulfuric acid. This is completely saturated neutral representation. Here it's with charge separations. These 2 are resonating forms. In such cases, one of the form contributes to the overall structure greater than the other one. So that is determined again by some rules, and I will explain this one by one here. The structure with a maximum of octets are most important. For example, in the case of nitric oxide, you have two resonating forms. This is one, and this is one, and this is one. And as per the guideline 1, the structures with maximum octets are most important. For example, if you see the nitrogen has one lone pair and a triple bond. Triple bond contributes to 6 electrons. 6 plus 2 is 8. So nitrogen is having octet configuration 8. Let's calculate for oxygen. So oxygen has got triple bond this side, so that means 6 electrons, and there is a lone pair. So this also has got octet configuration fulfilled. Let's calculate here. Nitrogen is now attached to oxygen through a double bond, which means only 4 electrons are involved in the bonding. So the 4 plus 2, it's only 6 electrons on nitrogen, which is not an octet configuration. Therefore, this is not a major contributor. This is a minor resonance contributor, and the nitric oxide predominantly exists in this form, and very little or very few fraction will exist in this form. Next example, next guideline is charges should be preferentially located on atoms with compatible electronegativity. So the example which I would like to give for this guideline is that acetate ion. Acetate ion, the negative charge can either center at oxygen or it can center at carbon. So now you have to compare which one has more electronegativity. Oxygen has more electronegativity or carbon has more electronegativity. Oxygen has more electronegativity, obviously, because it's on the right side in the periodic table of that of carbon. So since oxygen is more electronegative, it wants to retain negative charge with itself. So this will be the major contributor, or this will be the major resonance form, and this will be the minor contributor. Now this rule is actually contradicting guideline 2. This guideline 2 is actually contradicting guideline 1 if you compare the example, if you apply guideline 2 this nitric oxide. For example, in nitric oxide we said that NO plus is actually the major contributor and N plus this is minor contributor, but we know nitrogen is less electronegative than oxygen. So according to guideline, nitrogen should have the positive charge. That means this should have been the major contributor. In such cases, it says that rule 1 or guideline 1 is the predominantly deciding factor than guideline 2. So if the structure with the maximum octets are fulfilled, and that's okay, and the guideline 2 doesn't operate. So you can just ignore the guideline 2 in case if guideline 1 is satisfied. So now I'll go to the guideline 3, which says that structures with less separation of opposite charges are more important resonance contributors than those with more charge separation. For example, in formic acid, you can write both polarized as well as unpolarized form, and it says that the structure with no polarization is the major contributor, and the one with separations, charge separation, is the minor comparator, because it requires some energy to separate the charges. So that's the reason why this charge separated resonance form is not the major contributor. Okay. Now just I would like to give you a small activity. Please try to draw the resonating forms for CNO and NO minus. Also try to do the previous thing, that is the nitrite ion. Try to draw the structure of nitrite ion and find the geometry, whether it's a linear molecule or angular molecule, and then show the two resonating forms of nitrite ion. First you need to write the Lewis structure, electron dot formula of nitrite ion, and then explain whether it is having an angular structure or bent structure, and then show the two resonating forms of nitrite ion. It's quite an exercise, having learned all these Lewis structures, electron dot formula, and why the molecules are adopting different shapes, structures, and the different resonating forms, which is the contributing, try to apply all those on this one ion and see and compare yourself whether you are able to do correctly. I'll be explaining shortly after 5 minutes, but take your time and try to show the two resonating forms of nitrite ion with electron structure and the shape. And if also try to draw the resonance forms of the CNO minus molecule ion and then NO minus ion. The two resonating forms of the CNO minus and NO minus. After this exercise, then we are done. Then we can go, and we almost have, we are having about 30 minutes time. We can discuss any doubts that you have in great detail. First, I will show solve the problem of NO2 minus ion. So if you, as I said, first you need to write the Lewis electron dot formula for this. If you write the Lewis electron dot formula, it will come like this: oxygen, and then oxygen, nitrite. You have a lone pair in here. 1, 2, 3, 4, 1, 2. Like this. 3, 6, 8. It's like this. So you will have the electron structure like this. So basically, if you consider the electron repulsion theory, then you have to keep these three bonds. This is a double bond, this one, as far apart as possible. And since you don't have anything fourth one, so it doesn't need to have a tetrahedral structure. So you can easily accommodate trigonal structure because it of bond. So the bond angle is 120 degrees. If it's tetrahedral, then it's only 109. So in fact, this is a better structure than this one. And here, since you have only three bonds, so you can write one of them, consider that as a lone pair, and the other one is oxygen. The other oxygen is a double bond. So now if you use that fourth rule of Lewis structure, then one of the atom can have a negative charge. Nitrogen cannot have. If you just apply the rule, you will be able to find. Now this structure is actually a bent structure. It's not linear structure. So all those of you who have written a linear structure, it's wrong. This molecule is actually angular or bent. So since having written this as one of the forms, you can actually write a resonating form. This double bond migrates and this comes here. There's a lone pair there, and you can write nitrogen O minus, and it can have O, this one. So these are the two resonating forms of nitrite anion. So now we will do the other examples as well. So the second problem which I asked was draw the resonating forms of CNO minus and then NO minus. So even those also I will draw right now. So CNO, if you draw the Lewis acid structure and then find where the charge goes, all those exercises, so it will come N plus triple bond C, and there's a double bond and a negative charge O, and this one. And for you can also have resonating structures for this, that is C2 minus double bond N plus double bond O. Okay, and for NO minus N double bond O, you can have octet here. Similarly, nitrogen can have 2 lone pairs, a negative charge. So this can have a resonating form as well. Another resonating form is this, negative charge. Now we need to find which one is the major contributor, because both are not similar. In the case of nitrite, both are similar, so both are equal contributors. So in fact you can also write like this: O dot 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 dot, and then half minus, here another minus half. This you can write. Whereas in this case both are not equivalent, so we need to identify which one is the major contributor. Again, you need to use those three rules, and if you apply those three rules, here there are two negative charges, here the charges are quite spread, so this is the major contributor. And in this case, this N minus is preferred because nitrogen has the right hand side. This one, nitrogen has no octet. 1 2 3 4 5 6. This has only 6 electrons, whereas here everything is octet. 1 2 3 4, this is 4 8. So oxygen also, it has its own 4 and then 8, so this is 8. So this is the major contributor. Okay, now to summarize, today we have actually tried to understand the ionic and covalent bond difference between them, and we also have seen that these two are extreme examples, and in reality the molecules have polar covalent, some ionic bond have covalent character, and some covalent bond has polarization due to difference in electronegativity between the bonding atoms. And also we have seen that how to draw the electron dot formula, and using electron dot form we have drawn the structures, and by comparing the lone pair repulsions we can able to predict now what will be the structure of the molecules, whether it will be linear or whether it will be angular. Those information we could able to find, and we could also extend this for charged species like cations and anions, and we have lastly discussed these cations and anions can have different resonating forms. Sometimes it can be equivalent and sometimes it can be non-equivalent. In case of non-equivalent resonating forms, one of the form will be a major form, and there are rules which we have also seen some time back on how to decide which one will be the major contributing resonating structures. So with this I will conclude here, but in the next class I will go for a little higher level of theory called molecular orbital theory of bond structures. So we'll try to understand the bonding from the point of view of molecular orbital theory, which can address all the shortcomings of the classical theory which we all studied in school textbooks, and which will be able to address all these issues like octet rule is not followed for some molecules. I already explained. There are some other shortcomings of the existing the lower order theories, which all can be accounted by molecular orbital theory, which requires a little bit of understanding of quantum mechanics, which I'll explain in great detail in the next class. So with this I'll conclude, and we will now go open the session for any questions and further discussions on this. And thanks for this opportunity, and I look forward for any questions from all of you. Yes, is there any questions? Feel free to ask me any basic questions, anything, no problem. Thought so far, is it clear or not clear, or what do you feel about it? Because as a teacher I always try to take opinions from students, keep asking every class whether you understood, is there any problem. So please feel free to tell if there is even any problem or what you feel about, and I'm always open to questions. Students, I want students frankly ask me, sir, is very why we have to study chemistry. One student asked me, I'm a computer scientist, how chemistry is going to help me? So you can ask me any questions, because I already prepared for such questions. Someone asked me, how did you decided on formal charge and H3O plus? Okay, so I'll go back to the slides now. So for H3O plus, there are two choices. The positive charge can be on hydrogen or oxygen. First I took the case of hydrogen. So the rule is this: formal charge equal to number of valence electrons minus number of lone pair electrons minus half the number of bonding electrons. So the number of valence electron in hydrogen, we all know it has only one electron. So that I wrote one electron. Okay. And the number of lone pair electrons on hydrogen, if you write the Lewis structure for H2O, this is the Lewis structure. Hydrogen doesn't have a lone pair, or other words bonded pair of electrons, non-bonded pair of electrons. As you can see, there is no dots here. Hope you are able to see here. I hope you're able to see where the cursor is right now. So you can see hydrogen, there is no non-bonded electrons. So you can safely put as 0, no problem. And another thing is that the number of bonding electron divided by 2. So hydrogen has only one bond contributes to 2 electrons. So you write 2 and then the divided by 2 is already there. So if you do this, solve this, and you will get 0. So that since it's coming as 0, formal charge is 0 on hydrogen. So hydrogen cannot have any charge. Now we'll do it for the same exercise for oxygen. Oxygen, the number of valence electron in general, it's not in this molecule, but in general, oxygen has a valence of 6 electrons. That's why for oxygen, it is 1s2, 2s2, 2p4. So valence electron is this one, second shell. So 2 plus 4 is 6. So oxygen has 6 electrons in its valence shell. So I wrote as 6. And here the number of lone pair electrons minus number of lone pair electrons. If you see the Lewis structure of H3O plus, I should not put the O plus at this time, so I will remove this O plus. Okay. Anyway, so since I've already written here, I've already put the positive charge, but if you apply the first 3 rules of writing the Lewis structure, you will not put the positive charge there. Only the 4th rule decides where to put the positive charge. I'm not able to remove this positive charge at this moment, but at the moment you just assume the structure without this positive charge. So if you see this structure, it has 3 bonds and only one lone pair. Lone pair means non-bonded electrons. Lone pair of electrons. So one lone pair of electron contributes to 2 electrons. So that's why we wrote 2 here. So 6, just a minute. So 6 we know why we wrote, 2 we know why we wrote. And now if you see, we just have to write number of bonding electrons. If you see this Lewis structure, we have 3 bonds with oxygen, 3 high OH bonds, right? So each bond contributes to 2 electrons, so I wrote 6. So 6 by 2 is 3, 6 minus 2 is 4, 4 minus 3 is 5. Or in other words, you can also write 6 minus 2 minus 3 is 6 minus 5, that is plus 1. So oxygen can have a charge of plus 1, that's why we wrote plus 1 charge.
Sir, why octet rule is not always true?
Why?
It's not always. Octet rule is not always true.
Okay. Yeah, why octet rule is not always true? For example, in boron, the valence electron is only 5. Okay, and if it forms a bond, it can only form 3 bonds and not 4 bonds. So 3 bonds each contributes to 6 electrons. So it has so there is always a vacancy. So octet rule is actually not a rule that is imposed, it was brought in theoretically, it was an observation. Okay, in general it was found that when there is an octet configuration, it is stable. Okay, it's an observation, and some atoms intrinsically cannot fill that octet because boron has only 5 electrons in that, so 3 electrons, one orbital is always vacant. So there is no way you can make a bond. But there are molecules, it can form a weak coordinate bond and satisfy that extra vacancy also. So octet rule is not a rule which needs to be strictly followed, it's just an observation. People have observed that when there is an octet arrangement, it is stable. So that's why you find that is not always followed. In other words, I can also put it this way, that it's an observation. Based on that, people have concluded that if octet is there, it is stable. But it doesn't say why octet Why only octet? It doesn't say why octet rules are always octet configuration is always stable. That is why the theory which I discussed so far about bonding is not just sufficient to explain the bonding present in molecules. So you need a higher level of theory to explain or to understand bonding in molecules. So that higher level theory is called molecular orbital theory, which I will discuss next class. So you will be able to understand. There the theory is completely different. It doesn't talk about this arbitrary rules, octet rule and all these things. That theory is completely different. That theory can explain why, explain the nature of bonding present in molecules. And at the moment you just don't worry too much about it. And in tomorrow's class when I'm discussing, you'll be able to get this information clear, because the bonding theories which I discussed is not sufficient in itself to explain this thing. Is that okay?
Thank you. Thank you, sir.
Oh, thank you for asking question. I like questions. Is there any more questions? No questions? Okay, if there are no questions, then I conclude this session. So we'll meet tomorrow again.